When the James Webb Space Telescope opened its eyes in 2022, it found galaxies that shouldn't exist massive, mature stellar cities shining brilliantly when the universe was barely 300 million years old, mere infants by cosmic standards. These ancient giants appeared impossibly organized, chemically enriched with elements that required billions of years to forge, yet they existed when the cosmos had barely begun. Scientists are now facing an uncomfortable truth. Either our cosmic timeline is catastrophically wrong, or the early universe operated under rules of physics we don't yet understand. Join us as we explore how one telescope shattered decades of carefully constructed theory and forced astronomers to rewrite the first chapter of cosmic history. First, light. The James Webb Space Telescope opened its infrared eyes in the summer of 2022, and within hours, astronomers found themselves staring at data that made no sense. The telescope's first deep field image, released that July, revealed not just distant galaxies as expected, but ancient structures so fully formed, so impossibly mature, that they seemed to mock 13 billion years of cosmic evolution. These weren't the faint, irregular smudges that theory predicted for the early universe. They were galaxies with defined shapes, organized spiral arms, and stellar populations that suggested billions of years of development, except they existed when the universe itself was barely old enough to have produced a single generation of stars. Webb's primary mirror, a hexagonal array of gold-coated beryllium spanning 6.5 meters, was specifically designed to capture infrared light, the stretched, reddened wavelengths from objects so distant that the universe's expansion has pulled their light toward the red end of the spectrum. Every photon Webb collects has been traveling through space for most of cosmic history, carrying information about conditions that existed when the universe was a fraction of its current age. The telescope sits at Lagrange Point 2, roughly 1.5 million kilometers from Earth, in a stable gravitational pocket where it can observe the cosmos without interference from our planet's heat signature or the sun's glare. The first shock came from an object designated glass, Z13. Spectroscopic analysis revealed light that had been stretched by a redshift value exceeding 13, meaning this galaxy existed approximately 300 million years after the Big Bang. 300 million years sounds generous until you consider what needs to happen to build a galaxy. Stars must form from collapsing clouds of hydrogen and helium. Those stars must fuse lighter elements into heavier ones within their cores. Some must explode as supernovae, seeding space with the raw materials for new stellar generations. Gas clouds must collapse again, forming new stars, and these processes must repeat enough times to build the complex structures Webb observed. The standard model of galaxy formation, refined over decades of observation and simulation, suggested that early galaxies should be small, irregular collections of young stars, cosmic toddlers still learning to walk. Instead, Webb found what appeared to be fully mature galactic systems with stellar populations showing signs of chemical enrichment that should have required billions of years to develop. The light spectrum from these objects revealed the presence of heavier elements, carbon, oxygen, silicon, created only in the nuclear furnaces of stars and dispersed through supernova explosions. Yet the universe at that epoch had barely existed long enough for the first stars to form, let alone die and contribute their processed material to a second generation. What made the discovery truly unsettling was the sheer number of these impossible galaxies. Glass, Z13, wasn't an outlier or a measurement error. Webb's deep field observations revealed dozens of similar objects, each one challenging fundamental assumptions about how quickly matter could organize itself in the early universe. The galaxies appeared too bright, too massive, too structured for their supposed age. Some showed signs of active star formation at rates 10 times higher than modern galaxies could sustain. Others displayed the spectral signatures of stars that were already ancient, implying even earlier formation periods that shouldn't have existed. The telescope's instruments, its near-infrared camera, and spectrographs allowed astronomers to measure not just the distance to these objects but also their physical properties. Mass estimates derived from their brightness and structure suggested galaxies containing billions of solar masses worth of stars, assembled when the universe was supposedly still in its cosmic dark ages. That period after the Big Bang's afterglow faded but before the first stars ignited. The implications rippled through cosmology like a stone thrown into still water. If galaxies could form this quickly, this completely, then something fundamental about our understanding of time, matter, and cosmic evolution needed revision. The universe's timeline, carefully constructed from decades of observation and theory, suddenly looked provisional, incomplete, possibly wrong, too early. 300 million years after the Big Bang represents roughly 2% of the universe's current age, a cosmic eye blink in which almost nothing should have happened yet. The universe at this epoch existed in conditions so different from today that comparing them feels like describing a different reality altogether. Temperature maps from the cosmic microwave background, the afterglow of the Big Bang itself, show a universe that was remarkably smooth, with density variations of only 1 part in 100,000. These tiny ripples in the fabric of space represented the seeds from which all future structure would grow, but the seeds were barely planted, the soil still settling. Gravity works slowly when building galaxies. Even with dark matter providing additional gravitational scaffolding, the process of pulling together enough material to form a galaxy-sized structure takes time. First, dark matter must clump together into halos, creating gravitational wells deep enough to trap ordinary matter. Then hydrogen and helium gas, still hot from the Big Bang, must cool enough to collapse into these wells. As the gas compresses, pockets within it reach densities and temperatures sufficient to ignite nuclear fusion, creating the first stars. These population 3 stars, made purely from primordial hydrogen and helium, were likely massive and short-lived, burning through their fuel in mere millions of years before exploding. The wreckage from these explosions would seed their surroundings with heavier elements, allowing a second generation of stars to form with slightly more complex chemistry. But even this accelerated timeline, optimistic in its assumptions, struggles to produce anything resembling a mature galaxy within 300 million years. The galaxies Webb observed didn't just exist at this early epoch, they appeared to have already undergone multiple generations of star formation and evolution. Their light spectra showed absorption lines from elements like oxygen and carbon, elements that don't exist in nature until massive stars create them through nuclear fusion and then scatter them through supernova explosions. Computer simulations of galaxy formation, run on supercomputers using our best understanding of physics, consistently produce small, irregular proto-galaxies at this epoch. These simulations factor in dark matter distribution, gas cooling rates, stellar evolution timelines, and the feedback effects of supernova explosions that blow gas out of developing galaxies, temporarily halting star formation. The models have been refined over years to match observations from previous telescopes, which showed a gradual progression from small, irregular objects in the early universe to the large, structured galaxies we see nearby today. Webb's observations don't just challenge these models, they shatter them. Consider the logistics of building a galaxy containing 10 billion solar masses worth of stars in 300 million years. If star formation began immediately after the Big Bang, which it couldn't have, because the universe needed time to cool enough for atoms to form, you would need to convert roughly 33 solar masses of gas into stars every single year, continuously, for the entire 300 million year period. Modern galaxies form stars at rates between 1 and 10 solar masses per year. The most vigorous starburst galaxies, undergoing exceptional bursts of formation triggered by galactic collisions, might briefly reach 100 solar masses per year. Webb found galaxies that appeared to have sustained formation rates far exceeding even these extreme examples, maintained over timescales that should have been impossible. The implications extend beyond star formation rates. Galaxies aren't just collections of stars, they're complex systems with organized structures. Spiral galaxies have distinct arms, central bulges, and disk components that take billions of years to develop through gravitational interactions and dynamical evolution. The galaxies Webb observed showed signs of this structural maturity, implying not just rapid star formation but also accelerated dynamical evolution. Dark matter halos, which provide the gravitational framework for galaxies, need time to settle into stable configurations. Gas must cool and fall into regular rotation patterns. Stars must complete multiple orbits around the galactic center, their collective motion gradually organizing into coherent structures. All of this requires time. Time that simply didn't exist if these galaxies formed, when Webb's observations suggest they did. Time paradox. The cosmic timeline astronomers had constructed over decades operated like a carefully wound clock, each tick representing millions of years of gradual development, and Webb's observations threw a spanner directly into its gears. The paradox wasn't simply that galaxies existed earlier than expected, it was that they existed in forms that violated the sequential logic of cosmic evolution itself. To understand why this matters, you need to grasp how the universe builds complexity, because unlike human construction where you can bring in materials from elsewhere, the early universe had to create everything from scratch, in order, with no shortcuts available. After the Big Bang, the universe contained only hydrogen, helium, and trace amounts of lithium. These are the lightest elements, created in the first 3 minutes when temperatures were hot enough for nuclear fusion to occur throughout all of space. Everything heavier, every atom of carbon in your body, every oxygen molecule you breathe, every iron atom in Earth's core had to be manufactured inside stars through nuclear fusion. This process takes time, not just for individual stars to fuse lighter elements into heavier ones, but for those stars to complete their life cycles, explode, scatter their enriched material, and allow new stars to form from gas clouds now seeded with heavier elements. The first generation of stars, called population 3 stars, contain no metals at all. Astronomers use metals to mean any element heavier than helium. These primordial stars were likely enormous, perhaps 100 to 300 times the mass of our Sun, burning through their fuel in just a few million years before exploding as supernovae. Their deaths would have enriched their surroundings with the first heavy elements, allowing a second generation of stars to form with slightly more complex chemistry. These population 2 stars could live longer, burn more steadily, and their eventual deaths would add more heavy elements to the cosmic inventory. Webb found galaxies whose spectral signatures showed substantial metallicity, meaning significant amounts of heavy elements at redshifts, corresponding to 300 to 400 million years after the Big Bang. The light from these galaxies showed absorption lines from oxygen, carbon, and silicon, elements that require multiple generations of stellar evolution to produce in observable quantities. The paradox emerges when you calculate how long this should take. Even if population 3 stars formed immediately, which they couldn't have, and even if they all exploded simultaneously, which they wouldn't have, there simply wasn't enough time for multiple stellar generations to complete their cycles and enrich the interstellar medium to the levels Webb observed. The timeline becomes even more constrained when you factor in the reionization epoch, the period when the first stars and galaxies began producing enough ultraviolet radiation to reionize the neutral hydrogen that filled space. This process didn't happen instantly. It required enough luminous objects to form and persist long enough to flood the universe with ionizing radiation. Current models suggest reionization began around 200 million years after the Big Bang, and wasn't complete until roughly 700 million years afterward. Yet Webb found fully formed galaxies with mature stellar populations existing during the period when reionization should have just been beginning, implying those galaxies had already undergone substantial evolution before the universe had even finished transitioning from its dark ages. The mathematics of stellar evolution impose hard limits on how quickly this can proceed. A star like our Sun takes roughly 10 billion years to exhaust its hydrogen fuel. More massive stars burn faster a star 10 times. The Sun's mass might last only 20 million years, but the most massive stars, while short-lived, are also rare. Building a galaxy requires forming billions of stars across a range of masses, and the longer-lived stars take time to evolve to the point where their chemical composition becomes visible in spectral analysis. The galaxies Webb observed weren't just collections of young, massive stars burning bright and fast. Their spectra showed the signatures of evolved stellar populations, including stars that had moved off the main sequence and entered later stages of their lives. This creates a temporal impossibility. The observations demand that multiple generations of stars formed, evolved, and died within the first few 100 million years, enriching their galaxies with heavy elements and creating stellar populations with age distributions that should require billions of years to develop. Either the early universe formed stars at rates and efficiencies that violate our understanding of gas, physics, and gravitational collapse, or the first stars were fundamentally different from anything our models predict, or the timeline itself needs revision. None of these options fits comfortably with existing theory. The paradox isn't just that galaxies appeared too soon, it's that they appeared too complete, too chemically enriched, too evolved for the time available. Ancient giants. Massive galaxies in the early universe weren't supposed to exist. Full stop. And yet Webb's instruments repeatedly detected objects containing stellar masses equivalent to tens of billions of suns within the first 500 million years of cosmic history. The term massive galaxy in astronomy refers not to physical size, but to the total mass of stars it contains. And these ancient giants rivaled modern galaxies in their stellar content, despite existing when the universe was barely 3% of its current age. The sheer scale of matter that needed to be assembled into galactic structures within such a compressed time frame defies the gentle, gradual process of hierarchical assembly that underpins modern cosmology. Hierarchical assembly theory, the foundation of galaxy formation models, operates on a bottom-up principle. Small structures form first as dark matter clumps gravitationally, pulling in ordinary matter. These small halos merge over time, building progressively larger structures. Dwarf galaxies combine to form bigger galaxies, which themselves merge into even larger systems over billions of years. The Milky Way, for instance, has grown through countless mergers, absorbing smaller satellite galaxies throughout its history, and will eventually merge with Andromeda several billion years from now. This process is slow, messy, and requires vast amounts of time to produce the massive elliptical galaxies we observe in the modern universe. Webb found galaxies that appeared to have skipped this entire process. Objects like Sears 93316, confirmed through spectroscopic analysis, showed redshifts, placing them around 250 million years after the Big Bang, with stellar masses exceeding 10 billion solar masses. That's comparable to small elliptical galaxies in the present-day universe, galaxies that supposedly formed through billions of years of mergers and accretion. The presence of such objects in the early universe suggests either that gas could collapse into galaxies far more efficiently than thought possible, or that dark matter halos could assemble much faster than simulations predict, or both. The efficiency problem centers on how effectively gas can be converted into stars. In modern galaxies, only a small fraction of available gas becomes stars, typically around 1 to 3% efficiency. Most gas gets heated by stellar winds, supernova feedback, and radiation pressure, preventing it from collapsing further. This inefficiency is actually necessary to prevent galaxies from converting all their gas into stars too quickly. But the massive galaxies Webb observed in the early universe would have required star formation efficiencies of 10, 20, even 30% to build their stellar masses in the available time. Nothing in our understanding of gas physics suggests this is possible. Gas heated to high temperatures doesn't want to collapse. It expands, disperses, and resists the gravitational pull trying to compress it into star-forming regions. The dark matter framework adds another layer of complexity. Dark matter provides the gravitational scaffolding for galaxies, forming deep potential wells that trap ordinary matter. But dark matter halos don't appear instantly, they grow through gravitational collapse and merger, just like the galaxies they host. Simulations of cosmic structure formation, which have successfully reproduced the large-scale structure of the modern universe, predict that dark matter halos massive enough to host giant galaxies shouldn't exist in significant numbers until at least 500 million years after the Big Bang. Webb found massive galaxies substantially earlier, implying either that dark matter clumps more efficiently in the early universe than models suggest, or that the relationship between dark matter, halo mass, and stellar mass was fundamentally different in the ancient cosmos. Some of these ancient giants showed another peculiar feature. They appeared remarkably compact. While modern massive galaxies span hundreds of thousands of light-years, some of Webb's early massive galaxies appeared concentrated into regions only a few thousand light-years across. This compactness creates additional puzzles. Stars forming in such dense environments would interact gravitationally far more frequently than in modern star-forming regions, potentially disrupting the formation process or triggering unusual stellar evolution. The compactness also suggests these galaxies hadn't yet undergone the dynamical evolution that causes galaxies to expand and settle into more relaxed configurations over time. The chemical composition of these ancient giants raised eyebrows as well. Despite their youth, spectroscopic analysis revealed surprisingly high metallicities, abundances of heavy elements that normally accumulate gradually over many generations of stellar evolution. A galaxy that forms quickly in the early universe should be metal poor, dominated by population 2 or even population 3 stars with minimal heavy element content. Instead, Webb found ancient massive galaxies with chemical signatures suggesting substantial prior stellar evolution, as if they'd been building stars for billions of years when only hundreds of millions had elapsed. The presence of heavy elements requires not just star formation but stellar death specifically, enough time for massive stars to exhaust their fuel and explode, distributing their fusion products throughout the galaxy. Cramming this entire cycle into the early universe's compressed timeline stretches the limits of plausibility. Speed problem. Star formation in the early universe appeared to be operating at rates that shouldn't be physically possible, with some of Webb's observed galaxies converting gas into stars 10 to 20 times faster than the most vigorous starburst galaxies in the modern cosmos. The raw mechanics of stellar birth impose hard limits on how quickly this process can occur, limits rooted in the fundamental physics of gravity, gas pressure, and radiation. When a cloud of hydrogen and helium begins to collapse under its own gravity, it heats up as gravitational potential energy converts to thermal energy. This heat creates pressure that resists further collapse, establishing a delicate balance between gravity pulling inward and pressure pushing outward. Only when specific conditions are met, when the cloud becomes dense enough and cool enough, can gravity overcome this resistance and trigger runaway collapse into a protostar. Modern star-forming regions like the Orion Nebula convert roughly 1 to 3 solar masses of gas into stars per year across their entire volume. The most extreme starburst galaxies, typically triggered by galactic collisions that compress vast quantities of gas simultaneously, might briefly achieve rates of 100 solar masses per year. These are extraordinary events, unsustainable over long periods, because the intense radiation and stellar winds from newly formed stars heat and disperse the surrounding gas, temporarily shutting down further star formation. The galaxy's web observed in the early universe appeared to be sustaining formation rates of several hundred to over 1,000 solar masses per year, maintained not for brief bursts, but apparently for extended periods covering tens of millions of years. The physical problem centers on something called the Eddington limit, named after Arthur Eddington, who worked it out in the 1920s. When stars form, especially massive ones, they produce enormous amounts of radiation. This radiation exerts pressure on the surrounding gas through momentum transfer. Photons carry momentum, and when they're absorbed by gas particles, they push those particles away. The Eddington limit represents the maximum luminosity a star can sustain before radiation pressure overcomes gravity and blows away any infalling material. For the most massive stars, this limit is reached quite quickly, effectively capping how much mass they can accumulate and how many can form in a given region before their collective radiation begins preventing further star formation. Galaxy-scale star formation faces additional constraints beyond individual stellar limits. The gas must cool to collapse, but cooling mechanisms become less efficient at the temperatures and densities characteristic of the early universe. Molecular hydrogen, the primary coolant in modern star-forming regions, forms through slow chemical pathways that require dust grains to catalyze the reaction. But dust doesn't exist in the primordial universe. It's made of heavy elements produced in stellar interiors and dispersed through supernova explosions. The first generation of star formation would have proceeded without this cooling mechanism, relying instead on far less efficient atomic hydrogen cooling. This should have made early star formation slower, not faster, than modern rates. Webb's observations suggested the opposite. Spectroscopic analysis revealed ultraviolet emission signatures consistent with vast numbers of massive hot stars forming simultaneously. The intensity of certain emission lines, particularly hydrogen alpha and oxygen doublets, indicated ongoing star formation at rates that, if sustained, would have converted the entire gas reservoir of these galaxies into stars within 100 million years. Modern galaxies regulate their star formation through feedback mechanisms, supernovae, stellar winds, and radiation that heat and sometimes eject gas from the galaxy entirely. These processes create a self-regulating cycle where bursts of formation are followed by quiescent periods as the galaxy replenishes its gas supply. Early galaxies should have experienced even stronger feedback because the first stars were likely more massive and shorter-lived than typical stars today, producing more energetic explosions and stronger winds. The speed problem extends beyond raw formation rates to the question of gas supply. Building a galaxy with 10 billion solar masses of stars at a formation rate of 1,000 solar masses per year requires 10 million years of continuous formation, assuming perfect efficiency where every atom of gas becomes stellar material. But efficiency is never perfect. Modern galaxies convert only a small fraction of their gas into stars. Most remains in the interstellar medium or gets heated and expelled. If early galaxies operated at even 20% efficiency, which would be remarkably high, they'd need 50 million years of sustained formation. And that assumes they started with sufficient gas to begin with, gas that needed time to cool and collapse into galaxy-sized structures in the first place. Some researchers proposed that early star formation might have been fundamentally different, perhaps producing a top-heavy initial mass function where massive stars formed preferentially over low-mass ones. Massive stars are far more luminous per unit mass, so a population skewed toward them would appear brighter and form faster. But this creates its own problems. Massive stars die quickly, and their deaths in supernova explosions would have flooded their host galaxies with energy, potentially unbinding the remaining gas and terminating further formation. The speed at which Webb's early galaxies appeared to be building stellar mass seemed incompatible with the very physics that should have been regulating that process. Missing billions. Between the formation of the first stars and the appearance of mature galaxies like the Milky Way, cosmological models predicted a gradual progression spanning billions of years, yet Webb's observations revealed galaxies that appeared to have bypassed entire epochs of this expected evolution. The missing period wasn't a measurement error or an instrumental artifact, it represented real galactic maturity, appearing in an era when only primitive structures should have existed. Astronomers refer to this phenomenon as the missing link problem, though that undersells the severity of what Webb uncovered. This wasn't about finding a transitional fossil in the evolutionary chain, it was about discovering that the chain itself might not exist in the form we'd imagined. The expected evolutionary sequence ran something like this. Population 3 stars form from primordial gas around 200 million years after the Big Bang. These massive stars live briefly and explode, enriching small regions with the first heavy elements. Population 2 stars form from this slightly enriched gas over the next few 100 million years, living longer and contributing more elements through their deaths. Small proto-galaxies merge and grow through hierarchical assembly, gradually building larger structures. By around 1 billion years, recognizable disk and elliptical galaxies should exist, but still relatively small and actively assembling. Mature, massive galaxies with well-defined structures shouldn't appear until at least 2 to 3 billion years had elapsed. Webb found galaxies at redshifts of 10, 11, even 13, corresponding to times when the universe was between 300 and 500 million years old, that showed spectroscopic and morphological features characteristic of galactic populations billions of years. More evolved, these weren't just bright or massive, though they were often both. They displayed spectral signatures indicating multiple stellar populations with different ages and metallicities, the hallmark of galaxies that have undergone several cycles of star formation and chemical enrichment. Some showed evidence of dust, those tiny grains of carbon and silicon that form slowly from heavy elements over many stellar generations. Others exhibited structured morphologies, spiral arms, bulges, even hints of bars, features that require time to develop through dynamical processes. The dust observation alone posed a substantial challenge. Dust grains form primarily in the outer atmospheres of evolved stars, particularly asymptotic giant branch stars and supernovae. These grains then drift into the interstellar medium, where they catalyze the formation of molecules and cool gas clouds, enabling further star formation. Building significant dust reservoirs requires that many stars complete their life cycles, die, contribute their processed material, and allow time for grain formation and growth. The presence of dust in spectral observations from galaxies at redshift 11 suggested they'd already completed this cycle multiple times. But the time available from the Big Bang to these observations was only 400 million years, barely enough for even one full cycle, let alone the multiple iterations needed to create observed dust abundances. Chemical abundance patterns provided additional evidence of missing evolution. When astronomers analyze the spectrum of a galaxy, they can measure the ratio of different elements, oxygen to hydrogen, carbon to oxygen, nitrogen to carbon, and these ratios tell a story about stellar evolution history. Massive stars produce oxygen and die quickly. Intermediate mass stars produce carbon and nitrogen but take longer to contribute these elements to the interstellar medium. The ratios between these elements act as clocks, revealing how many generations of each type of star have lived and died. Webb's early galaxies showed abundance patterns suggesting multiple generations of stars spanning a range of masses, implying evolutionary timescales far longer than the age of the universe when these galaxies existed. Morphological maturity presented another puzzle. Galaxies don't form with nice spiral arms or smooth elliptical shapes. They achieve these structures through long processes involving gravitational interactions, differential rotation, and dynamical relaxation. When two proto-galaxies merge, the result is initially chaotic, with tidal tails of stars stretched across vast distances and irregular, lumpy distributions of matter. Only after hundreds of millions to billions of years does this settle into organized structure. Yet some of Webb's early galaxies appeared remarkably ordered, with symmetric morphologies and regular features that suggested they'd already completed this settling process. The dynamical argument goes deeper than appearance. For a spiral galaxy to maintain its arms, the disk must achieve a stable rotation pattern, where stars orbit at velocities balanced precisely by the gravitational potential of all the matter in the galaxy. This requires time for stars to complete multiple orbits, averaging out their random motions into organized rotation. A star in the outer regions of a galaxy the size of the Milky Way takes about 200 million years to complete one orbit. For a disk to achieve stable structure, stars need to complete at least several orbits. The galaxies Webb observed at 300 to 500 million years after the Big Bang would have had time for at most 2 or 3 orbital periods, assuming they formed their disks immediately at the Big Bang, which they didn't, because matter needed time to collapse into galactic structures in the first place. The organizational maturity these galaxies displayed simply didn't match the dynamical time available. Glass, Z13. A single galaxy-designated glass, Z13, shattered the distance record and forced astronomers to reconsider whether their cosmic timeline was fundamentally mistaken. The object appeared in Webb's first deep field observations as an unremarkable reddish smudge, one among thousands of distant galaxies scattered across the image. But when spectroscopic analysis measured its redshift, the stretching of light caused by the universe's expansion, the number came back as 13.1. That single measurement placed this galaxy at a time just 300 million years after the Big Bang, roughly 30 million years earlier than any confirmed galaxy before it. The margin might sound modest, but in the early universe where every million years represents a significant fraction of cosmic history, 30 million years is an eternity. GLASS stands for Grism Lens Amplified Survey from Space, a collaborative program designed to use gravitational lensing, where massive galaxy clusters bend and magnify light from more distant objects to study the earliest cosmic structures. The survey targeted galaxy cluster Abell 2744, whose immense gravitational field acts as a natural telescope, bending and brightening light from galaxies billions of light-years beyond it. Without this lensing magnification, GLASS, Z13 would have been far too faint for even Webb to detect. The cluster's gravity stretched and amplified the galaxy's light by a factor of roughly 2, making the impossible merely extraordinarily difficult to observe. The spectroscopic data revealed more than just distance. GLASS, Z13's light spectrum showed clear signatures of ongoing star formation, with emission lines indicating the presence of hot, young stars ionizing their surrounding gas. The galaxy wasn't particularly massive by modern standards. Estimates suggested a stellar mass around 1 billion times the Sun, making it roughly 1% the size of the Milky Way. But mass wasn't the issue. The problem was that this billion solar mass galaxy existed when the universe had barely cooled enough for atoms to form, let alone collapse into stars, and those stars to assemble into gravitationally bound galactic structures. The formation timeline became more puzzling when researchers calculated backward from the observed properties. Building a billion solar mass galaxy requires forming stars continuously over some extended period. Even at aggressive formation rates of 100 solar masses per year, 10 times what the Milky Way currently sustains, you'd need 10 million years of uninterrupted star formation. That might seem manageable within a 300 million year window until you account for everything that must happen first. The universe spent its first few 100,000 years too hot for atoms to exist. Radiation and matter existed as a plasma where electrons couldn't bind to nuclei. Only after this period could neutral hydrogen form, and only after hydrogen formed could gravity begin pulling it into the dense clumps that would eventually become stars. The first stars themselves, population 3 stars made purely from hydrogen and helium, needed time to form from these density fluctuations. Dark matter provided the gravitational scaffolding, but ordinary matter had to cool and collapse into the dark matter halos, a process that doesn't happen instantaneously. Once the first stars formed, they needed to live out their lives and die, enriching their surroundings with heavier elements that would allow subsequent generations of stars to form more efficiently. Glass, Z13's spectrum, showed clear evidence of these heavy elements, meaning it couldn't be composed entirely of first-generation stars. Multiple stellar cycles had already occurred. The galaxy's morphology added another layer of intrigue. High-resolution imaging revealed not a chaotic blob of young stars, but a relatively compact, organized structure with a defined shape. The object measured roughly 2,000 light-years across, tiny compared to modern galaxies, but remarkably coherent for something that supposedly assembled in cosmic record time. This compactness suggested the stars weren't just forming randomly throughout a diffuse gas cloud, but had already settled into a gravitationally bound system with organized dynamics. Stars in such a system need time to complete orbits around the galactic center, averaging out their random velocities into coherent rotation. A star at the edge of glass, Z13, would take roughly 10 million years to complete one orbit, a not insignificant fraction of the time available since the Big Bang, when accounting for all the prerequisite stages of cosmic evolution. What truly distinguished glass, Z13, wasn't any single extraordinary property, but rather the combination of distance, mass, structure, and chemical composition. Each aspect individually might have been explained through some optimistic but plausible scenario. Together, they painted a picture of accelerated evolution that seemed to violate the leisurely pace at which the early universe should have assembled its first galaxies. The galaxy stood as physical evidence that the universe's opening act proceeded far more quickly than the script predicted, leaving astronomers to wonder whether they'd misunderstood the production schedule entirely, or if glass, Z13, represented something genuinely anomalous, an outlier whose formation benefited from conditions or processes not yet incorporated into theoretical models. Wrong metals. Heavy elements appeared in the spectra of Webb's earliest galaxies, decades of millions of years before stellar evolution should have produced them, presenting a chemical impossibility that undermined our understanding of cosmic nucleosynthesis. The term metals in astronomy encompasses everything heavier than helium, carbon, oxygen, silicon, iron, all the elements essential for planets, life, and the complex chemistry that makes the universe interesting. None of these existed at the Big Bang. The universe's first 3 minutes produced only hydrogen, helium, and traces of lithium through primordial nucleosynthesis, the brief window when temperatures throughout space were high enough for nuclear fusion to occur. Everything else had to be manufactured inside stars, element by element, through nuclear processes that take time. The manufacturing works like this. Hydrogen fuses into helium in stellar cores, releasing energy that keeps stars shining. Once a star exhausts its hydrogen, if it's massive enough, its core contracts and heats until it's hot enough to fuse helium into carbon. More massive stars continue this process, building oxygen, neon, magnesium, silicon, and eventually iron through successive stages of fusion. Each stage requires higher temperatures and pressures, and each produces less energy than the previous stage. Iron represents the end of this road. Fusing iron consumes energy rather than releasing it. So once a massive star's core fills with iron, fusion stops, the core collapses catastrophically, and the star explodes as a supernova. These explosions both create elements heavier than iron through rapid neutron capture and scatter all the processed material back into space, enriching the interstellar medium for future stellar generations. This entire cycle requires time not just for individual stars to evolve and die, but for enough stars to complete the cycle that their collective contributions significantly enrich a galaxy's gas supply. A massive star might complete its evolution in a few million years, but building up substantial metallicity across an entire galaxy requires thousands or millions of such stars to form, live, and die. Intermediate mass stars contribute different elements on longer timescales. Stars like the Sun take billions of years to reach the stages where they produce significant carbon and nitrogen. The metallicity of a galaxy thus serves as a clock, recording the cumulative history of stellar evolution within that system. Webb's observations revealed oxygen and carbon signatures in galaxies at redshifts above 10, existing just 400 million years after the Big Bang. Oxygen forms in massive stars during helium and carbon burning, while carbon is produced both in massive stars and through helium burning in intermediate mass stars. The presence of these elements in observable quantities implied that numerous stellar generations had already cycled through formation, evolution, and death. The oxygen to hydrogen ratio in some of these early galaxies approached 1/10 the solar value, meaning they'd already accumulated metallicity equivalent to 10% of what our Sun possesses. Despite the Sun having formed billions of years later with the benefit of countless preceding stellar generations, the chemical evolution models that successfully reproduce metallicity patterns in modern and nearby galaxies break down when applied to these Webb observations. These models factor in star formation rates, the initial mass function of stars, stellar lifetimes, supernova rates, and how efficiently newly formed elements mix into the interstellar medium. When you input the properties of Webb's early galaxies, their ages, masses, and observed metallicities, the models consistently demand more time than the universe had existed. Either stars in the early universe formed and died far more rapidly than physics suggests possible, or the efficiency of metal production and distribution was orders of magnitude higher than we observe in any modern system. One proposed resolution involves population 3 stars, those first-generation objects formed from primordial gas. Theoretical models suggest these stars might have been extraordinarily massive, perhaps 100 to 300 solar masses, and correspondingly short-lived, completing their entire evolution in less than 2 million years. If the earliest star formation preferentially produced these giants, you could potentially cycle through multiple stellar generations quickly. But this creates new problems. Such massive stars would produce unusual chemical patterns, with peculiar ratios of elements that don't match what Webb observes. They'd also generate enormous amounts of energy through their deaths, potentially disrupting their host galaxies and terminating further star formation. The metallicity problem extends beyond simple abundance. Different elements form in different stellar environments and on different timescales, so their relative abundances encode information about a galaxy's star formation history. Nitrogen, for instance, is primarily produced in intermediate mass stars on longer timescales than oxygen, which comes mainly from massive short-lived stars. The nitrogen to oxygen ratio therefore acts as another clock, revealing the relative contributions of different stellar populations. Some of Webb's early galaxies showed nitrogen to oxygen ratios suggesting contributions from both massive and intermediate mass stars, implying stellar populations spanning a range of masses and ages, a level of chemical sophistication that should have required hundreds of millions to billions of years to develop, not the few 100 million actually available. Brightness mystery. Luminosity measurements from Webb's earliest galaxies registered values that violated basic constraints on how bright objects could possibly be at their observed ages, creating a puzzle that touched the fundamental physics of stellar radiation. When astronomers measure a galaxy's brightness, they're not just counting photons, they're calculating the total energy output across all wavelengths, a quantity that directly correlates with stellar mass and star formation activity. Modern galaxies follow predictable luminosity patterns based on their stellar populations. Young, actively forming galaxies shine brightly in ultraviolet light from hot massive stars. Older quiescent galaxies glow predominantly in infrared from cool evolved stars. The relationship between a galaxy's mass, age, and brightness forms a well-established framework that's held across billions of years of cosmic history. Webb's early galaxies ignored this framework entirely. Several objects detected at redshifts above 11 showed ultraviolet luminosities equivalent to galaxies containing 10 to 20 billion solar masses of young stars, yet their spectra and other properties suggested stellar masses of only 1 to 2 billion solar masses. The discrepancy meant these galaxies were somehow producing 5 to 10 times more light per unit stellar mass than should be physically achievable. Stellar luminosity isn't arbitrary. It's determined by nuclear fusion rates in stellar cores, and those rates depend directly on stellar mass and composition. A star's brightness scales roughly with the 4th power of its mass, meaning a star twice as massive shines 16 times brighter, but there are limits. The most massive stars that can stably form top out around 100 to 150 solar masses, beyond which radiation pressure prevents further mass accumulation. If you pack a galaxy with nothing but these maximum mass stars, you achieve the highest possible luminosity to mass ratio. Even this extreme scenario, which has never been observed in any real galaxy, couldn't account for the brightness Webb measured in some early objects. The implication was that either these galaxies contained stellar populations unlike anything in the modern universe, or some additional energy source beyond stellar fusion was contributing to their luminosity. Active galactic nuclei, supermassive black holes accreting matter and releasing enormous energy, can boost a galaxy's brightness, but identifying AGN requires specific spectroscopic signatures, and many of the overluminous galaxies showed no such signatures. The brightness problem deepened when researchers examined the spectral energy distribution, how the light was divided across different wavelengths. Overluminous galaxies didn't just appear too bright, they appeared too bright in specific ways that didn't match any known stellar population. Some showed excessive ultraviolet emission without corresponding infrared excess, suggesting the presence of extremely hot stars far more numerous than star formation theory predicts. Others displayed peculiar emission line ratios indicating ionization states that require vast amounts of energetic radiation, more than their stellar mass could plausibly generate. One proposed explanation involved top-heavy initial mass functions, the distribution of stellar masses at birth. Normal star formation produces mostly low-mass stars for every star like the Sun. Hundreds of smaller red dwarfs form, but low-mass stars contribute little to a galaxy's luminosity, because they burn their fuel slowly and shine dimly. If early galaxies preferentially formed massive stars, skewing the mass distribution toward the high luminosity end, you could achieve higher brightness per unit mass. The difficulty is that we've never observed such a skewed distribution anywhere, and theoretical models of star formation consistently predict bottom-heavy mass functions, where low-mass stars dominate numerically. The physics of star formation actively works against producing many massive stars. When a molecular cloud fragments into protostars, radiation pressure from the first massive stars to form tends to disrupt the remaining cloud, preventing further massive star formation. Feedback mechanisms that limit massive star production in modern galaxies should have been even stronger in the early universe, where the first stars likely formed in smaller, more fragile structures. Yet the brightness measurements demanded not just that massive stars formed in unusual abundance, but that they did so consistently across numerous early galaxies spanning hundreds of millions of years of cosmic history. Another curiosity emerged from variability studies. Some of Webb's bright early galaxies showed luminosity changes over observing periods spanning just months, impossibly rapid for variations driven by stellar evolution or even supernovae, which typically brighten and fade over weeks to months. Rapid variability generally indicates compact sources, either very massive stars undergoing unstable pulsations or accretion onto black holes. The presence of supermassive black holes in galaxies barely 300 million years old created its own timeline problems, as black hole growth theories suggested these objects needed hundreds of millions to billions of years to accumulate masses of millions or billions of suns. Stellar impossibility. The first generation of stars couldn't have formed until certain preconditions were met, yet Webb detected galaxies whose stellar populations appeared to predate these prerequisites, creating temporal contradictions that challenge the sequential logic of cosmic evolution. After the Big Bang, the universe expanded and cooled, but it remained ionized, a plasma of free electrons and atomic nuclei for roughly 380,000 years. During this epoch, photons couldn't travel freely because they constantly scattered off free electrons. Only when temperatures dropped enough for electrons to bind permanently to nuclei, forming neutral hydrogen atoms, did light decouple from matter. This moment, called recombination, marks the origin of the cosmic microwave background, the oldest light we can observe directly. Following recombination came the cosmic dark ages, a period lasting from roughly 400,000 to 100 million years after the Big Bang, when no stars existed yet, and the universe sat in darkness, filled with neutral hydrogen slowly collapsing under gravity into the first dark matter halos. These halos, formed from the gravitational clumping of dark matter, provided the potential wells necessary for ordinary matter to accumulate. But dark matter halos don't appear instantaneously, they grow through gravitational collapse, a process governed by the density fluctuations imprinted during inflation and amplified over time by gravity. Small halos form first, then merge into progressively larger structures. The first stars could only form once several conditions aligned. Dark matter halos massive enough to trap significant amounts of gas that had cooled sufficiently to collapse further, and densities high enough to trigger fusion. The cooling requirement presented particular challenges because the primordial gas contained only hydrogen helium, and trace lithium, no molecules, no dust, nothing that cools efficiently at the temperatures and densities of early halos. Molecular hydrogen, which forms when two hydrogen atoms bond, provides the primary cooling mechanism, but creating molecular hydrogen from atomic hydrogen is slow and inefficient without dust grains to catalyze the reaction. Theoretical models consistently place the formation of the first stars at roughly 100 to 200 million years after the Big Bang, with substantial uncertainties in that estimate, depending on assumptions about dark matter, halo growth rates, and gas cooling efficiency. Webb detected galaxies containing multiple stellar populations, stars of different ages and metallicities at 300 million years, implying not just that the first stars formed, but that they'd already lived, died, enriched their surroundings, and enabled second-generation star formation, all within a window that barely accommodated first-generation formation in the first place. The stellar impossibility extended beyond timing to the question of how these early systems assembled. Stars don't form individually in isolation. They form in clusters when molecular clouds fragment. A typical stellar cluster might contain hundreds to thousands of stars spanning a range of masses. The most massive stars in such clusters live only a few million years before exploding, while lower mass stars can persist for billions of years. The age distribution of stars within a galaxy thus encodes information about when different episodes of star formation occurred. Webb's spectroscopic observations revealed early galaxies with stellar populations showing evidence of extended star formation histories, not a single burst of formation, but multiple episodes separated by tens of millions of years. This implied that galaxy formation in the early universe wasn't a simple, monolithic process where a proto-galaxy formed its stars in one event and then evolved passively. Instead, these early systems apparently underwent multiple cycles of star formation, possibly triggered by gas accretion or minor mergers with smaller systems. Each cycle requires sufficient gas to collapse and form new stars, plus recovery time between cycles as stellar feedback heats and disperses gas. The presence of such complex star formation histories in galaxies at 300 to 400 million years demanded that galaxy assembly began substantially earlier, potentially within the first 100 million years, to allow time for multiple formation cycles. Population 3 stars, those first stars formed from absolutely pristine gas with no heavy elements, represented another complication. These objects should have been extraordinarily massive due to the inefficient cooling of primordial gas, perhaps 100 to 300 times the Sun's mass. Such stars would burn through their fuel in less than 2 million years and explode as pair instability supernovae, leaving no remnant. Their deaths would immediately enrich their surroundings with the first heavy elements. Webb's early galaxies showed metallicity levels suggesting numerous population 3 stars had already completed this cycle, but the timescale available from the Big Bang to these observations barely exceeded the lifespan of even the most massive population 3 candidates. Rewriting history. Decades of carefully constructed cosmic history collapsed within months of Webb's first observations, forcing astronomers to fundamentally reconsider the narrative arc they'd spent careers building about how the universe evolved from simplicity to complexity. The standard cosmological model, lambda CDM, had successfully explained observations ranging from the cosmic microwave background to the large-scale structure of galaxies, predicting with remarkable accuracy how the universe should look at different epochs. This model described a leisurely progression where structure grew slowly from tiny density fluctuations, with galaxies gradually assembling through mergers and accretion over billions of years. Every telescope before Webb had confirmed this picture, each observation fitting neatly into the established timeline, like pieces completing a vast jigsaw puzzle. Webb's observations didn't just add new pieces, they revealed that significant portions of the puzzle had been assembled incorrectly. The telescope's infrared sensitivity and unprecedented resolution allowed it to peer into epochs that previous instruments could barely glimpse, and what it found there contradicted expectations so thoroughly that researchers initially questioned whether the data could be trusted. Early suspicions focused on potential systematic errors in redshift measurements or photometric calibrations. Perhaps the objects weren't as distant as they appeared. Perhaps the light had been gravitationally lensed and amplified in ways that skewed brightness estimates. But as more observations accumulated and independent analyses confirmed the findings, the uncomfortable truth settled in the observations was solid. and the model needed revision. The implications rippled outward from galaxy formation into related fields. Structure formation theory, which describes how gravitational collapse transforms smooth, primordial density fields into the lumpy universe we inhabit, suddenly faced challenges explaining how such large structures could assemble so quickly. Dark matter physics, which provides the gravitational scaffolding for galaxy formation, came under scrutiny. Perhaps dark matter behaves differently in the early universe, clumping more efficiently than current models suggest. Stellar evolution theory confronted uncomfortable questions about whether the first stars formed differently enough to accelerate chemical enrichment beyond standard predictions. The textbooks would need rewriting, but more fundamentally, the conceptual framework astronomers used to think about cosmic evolution required adjustment. The old narrative placed galaxy formation as a gradual process beginning around 400 to 500 million years after the Big Bang, with small proto-galaxies slowly building into the majestic spirals and ellipticals we see today. Webb's discoveries suggested that robust galaxy formation began substantially earlier, possibly within the first 200 million years, and proceeded far more rapidly than models allowed. This compression of the timeline meant that processes astronomers thought unfolded over billions of years might have completed in hundreds of millions. Theorists scrambled to adjust models, tweaking parameters to accommodate the new observations. Gas cooling rates were increased to allow faster collapse. Star formation efficiencies were boosted to produce more stars from the available gas. Initial mass functions were skewed toward massive stars to generate more luminosity per unit mass. But these adjustments often created new problems. More efficient cooling requires molecules or dust that shouldn't exist yet. Higher star formation rates trigger stronger feedback that should disrupt galaxies. Top-heavy mass functions produce unusual chemical signatures not observed. Each attempted solution seemed to solve one problem while creating others. Some researchers proposed more radical revisions. Perhaps the lambda CDM model's assumptions about dark energy or the expansion rate needed modification. If the universe expanded slightly differently in its earliest epochs, it might allow more time for structure formation than the standard model suggests. Others suggested that reionization, the process where the first stars ionized the hydrogen-filling space, occurred earlier and more rapidly than thought, fundamentally changing the environment in which early galaxies formed. These proposals moved beyond adjusting parameters within the existing framework to questioning the framework itself. The sociological impact within astronomy proved nearly as significant as the scientific impact. Graduate students who'd spent years running simulations based on lambda CDM parameters suddenly found their work obsolete. Researchers whose careers focused on understanding how galaxies formed in the standard picture now grappled with observations that contradicted their life's work. Yet there was also excitement. Genuine puzzles are rare in mature fields, and Webb had delivered a genuine puzzle. The early universe, which many thought was fairly well understood, had become mysterious again. Conference presentations shifted from presenting results that confirmed expectations to wrestling with observations that defied explanation. Collaboration patterns changed as observers with Webb data teamed with theorists trying to make sense of it. New working groups formed specifically to address the early galaxy problem. Funding agencies began prioritizing proposals aimed at understanding Webb's discoveries. Within 2 years of the telescope's launch, the field's entire research trajectory had pivoted to confront the reality that the universe's opening chapters needed to be rewritten from scratch. With the humbling acknowledgement that the cosmos operates on timescales and through processes we're only beginning to properly comprehend. Before time, Webb's deepest observations effectively functioned as archaeological excavations into an era when the universe was still settling into the physical laws and structures that would govern its future evolution, revealing conditions so foreign to modern experience that describing them requires rethinking what words like space, time, and formation even mean. The first few 100 million years after the Big Bang represent not just an earlier epoch, but a fundamentally different regime of physics, where processes that would later take billions of years to unfold compressed into cosmic instants, where the distinction between formation and evolution blurred into a continuum, and where the seeds of everything that would follow were planted in soil still cooling from creation's heat. At 300 million years, the universe had expanded to roughly 2% of its current size. This compactness had profound implications. Galaxies that today sit billions of light-years apart were separated by mere millions of light-years, close enough to interact gravitationally far more frequently than modern galaxies do. The cosmic web of dark matter filaments, which today spans hundreds of millions of light-years between dense nodes, was proportionally compressed, making the universe a far denser, more interconnected place. Material could flow between protogalaxies more easily. Mergers and interactions happened more frequently. The entire cosmos resembled a densely packed city compared to the suburban sprawl of the present-day universe. Temperature gradients tell another part of this story. The cosmic microwave background, which today has cooled to a frigid 2.7 Kelvin above absolute zero, radiated at nearly 8 Kelvin, when the universe was 300 million years old, still cold by human standards but representing 3 times the thermal energy density. This radiation filled all of space, providing a bath of infrared photons that interacted with gas and influenced its thermal properties. The intergalactic medium itself was warmer, having cooled from the Big Bang's initial heat for only a cosmic moment. These higher temperatures affected how gas could cool and collapse paradoxically. A warmer universe in some ways facilitated faster structure formation, because the longer wavelength of thermal radiation meant gas could radiate energy more efficiently under certain conditions. The chemical composition of everything differed fundamentally from the modern universe. The periodic table as we know it barely existed. Almost everything was hydrogen and helium, with only the faintest traces of heavier elements produced in the cores of the first short-lived massive stars. The absence of metals had cascading effects. Without dust grains, gas clouds couldn't cool efficiently through molecular hydrogen formation. Without carbon and oxygen, certain chemical pathways that regulate star formation in modern galaxies didn't exist. The stars that formed in this environment likely had properties unlike any stars we can observe directly in the present-day universe. They might have been more massive, hotter, and shorter-lived, producing the intense radiation fields and chemical enrichment Webb detected in early galaxies. Dark matter's role in this epoch remains somewhat mysterious despite its dominance. The dark matter halos that would eventually host galaxies were still assembling, growing through constant mergers of smaller halos. The violence of this process cannot be overstated. When dark matter halos collide, they pass through each other, because dark matter doesn't interact electromagnetically, but the ordinary matter trapped within those halos collides violently, heating and sometimes shocking into rapid star formation. Early galaxies existed in a state of constant bombardment, fed by streams of cold gas flowing along dark matter filaments, while simultaneously being battered by mergers that triggered bursts of star formation. The distinction between formation and evolution loses meaning when galaxies are constantly being assembled and disassembled by ongoing mergers. Webb's observations captured light from this chaotic period, photons that began their journey when the universe looked nothing like the organized, mature cosmos we inhabit. These photons travelled through expanding space for over 13 billion years. Their wavelengths stretched from ultraviolet and visible light into the infrared that Webb was designed to detect. Each photon carries encoded information about the conditions in which it was emitted, the temperature of stars, the chemistry of gas clouds, the distribution of dust, the rate of star formation. Decoding this information allows astronomers to reconstruct not just what the early universe looked like, but how it functioned, what processes dominated, and how rapidly change occurred. The philosophical implications of studying this epoch extend beyond astronomy into questions about the nature of time itself. When we observe galaxies at redshift 13, we're not just looking at distant objects, we're observing the universe when it was fundamentally younger, when fewer processes had occurred, when less history had accumulated. In a real sense, Webb allows us to witness the universe before it had fully become itself, before the structures and patterns that define cosmic architecture had fully crystallized. The discoveries suggest that this crystallization happened far more rapidly than expected, that the universe rushed into organization with surprising speed, and, as if eager to begin the long story of cosmic evolution that would eventually lead to stars, planets, and creatures capable of looking back through telescopes at their own ancient origins. Expansion question. The rate at which the universe has been expanding since the Big Bang might not have followed the smooth, predictable trajectory that cosmologists had confidently mapped for decades. and Webb's observations of impossibly early galaxies have forced researchers to consider whether space itself grew differently in those first few 100 million years than our models assume. The expansion rate, quantified by a number called the Hubble constant, determines how quickly galaxies recede from one another and fundamentally sets the timeline for cosmic evolution. Measure the expansion rate incorrectly, and every distance estimate, every age calculation, every evolutionary timescale becomes systematically skewed. For years, astronomers thought they'd nailed down this number through multiple independent methods: observations of nearby supernovae, measurements of the cosmic microwave background, studies of distant quasars. The values from different methods didn't quite agree, creating what's called the Hubble tension, but the discrepancies seemed manageable. Webb's early galaxy observations added a new dimension to this tension. If galaxies at redshift 13 truly existed 300 million years after the Big Bang, and if they truly contained the stellar masses and showed the evolutionary maturity that spectroscopy suggested, then either our understanding of galaxy formation is catastrophically wrong, which seems increasingly unlikely given how many independent lines of evidence point to the same conclusion, or the universe provided more time for this evolution than standard cosmology allows. More time doesn't mean the universe is older than we think. The cosmic microwave background provides an independent measure of the universe's age that's quite robust. Instead, it means the early universe might have expanded more slowly than currently modelled, giving structure formation processes additional time to operate within a fixed cosmic age. The mathematics of cosmological expansion depend critically on the energy content of the universe. The standard lambda CDM model assumes specific proportions of ordinary matter, and dark energy, with each component contributing differently to expansion. Dark energy accelerates expansion. Matter decelerates it through gravitational attraction. The balance between these components changes over cosmic history in the early universe. Matter dominated and expansion decelerated significantly. Later, as the universe expanded and matter density dropped, dark energy came to dominate, causing the current accelerated expansion. If these proportions differed slightly in the early universe, or if dark energy behaved differently then, the expansion rate could have been slower during the critical first few 100 million years. Some theorists propose that dark energy might not be the constant cosmological parameter we've assumed, but instead a dynamic field that changes over time. In these models, dark energy in the early universe contributed less to expansion than it does today, allowing the universe to expand more slowly. This slower expansion would have several consequences. Galaxy formation timescales would effectively stretch out 300 million years of slow expansion, provides more time for processes to occur than 300 million years of rapid expansion. The higher matter density that results from slower expansion also enhances gravitational collapse, potentially allowing structures to form more efficiently. Gas cools and collapses faster in denser environments. Dark matter halos assemble more quickly when matter densities are elevated. Modifications to expansion history create testable predictions. The cosmic microwave background, that snapshot of the universe at 380,000 years old, encodes information about expansion rates and energy densities through precise patterns in its temperature fluctuations. Measurements from the Planck satellite map these patterns with extraordinary precision, and while they're consistent with standard lambda CDM, small tweaks to dark energy's early behavior might fit the data equally well, while also accommodating Webb's observations. The challenge lies in finding modifications that solve the early galaxy problem without breaking the many other successful predictions of standard cosmology. Another approach questions whether our distance measurements are as reliable as assumed. Converting a galaxy's redshift into distance and age requires knowing the expansion history. If that history is wrong, our distance scale is wrong. Some of Webb's early galaxies might not be quite as distant, and therefore not quite as young as their redshifts suggest if expansion rates were different than modelled. A galaxy at redshift 13 might have formed 400 million years after the Big Bang rather than 300 million in a modified expansion scenario, buying precious additional time for stellar evolution and chemical enrichment. While this doesn't solve all the timeline problems, it eases them considerably. The expansion question extends beyond galaxy formation into the very nature of cosmic time. Redshift measures how much the universe has expanded between emission and observation of light, but translating that expansion factor into elapsed time requires assumptions about expansion rates throughout the interval. If those rates varied differently than assumed, our cosmic clock might need recalibration. The early universe's timeline, the dates assigned to first stars, first galaxies, reionization, and other landmark events all derive from models of expansion. Webb's observations suggest those dates might need revision, not because the observations are wrong, but because the framework used to interpret them requires adjustment to accommodate the reality of what actually occurred in those distant ancient epochs. Dark Ages. Darkness dominated the universe for roughly 100 million years after the first atoms formed, a period when no stars existed to illuminate the vast hydrogen clouds, settling slowly under gravity's patient pull, and Webb's observations are finally casting light, metaphorically speaking, into this lightless epoch that had remained inaccessible to every previous telescope. The cosmic dark ages began at recombination, when electrons combined with protons to form neutral hydrogen atoms roughly 380,000 years after the Big Bang. Before this moment, the universe was ionized plasma, where photons scattered constantly off free electrons, making space opaque to light. After recombination, photons could travel freely, creating the cosmic microwave background we observe today, but those photons quickly redshifted into the infrared and eventually radio wavelengths as the universe expanded, leaving visible darkness. What filled this darkness was hydrogen, vast quantities of neutral atomic hydrogen distributed according to the tiny density fluctuations imprinted during the universe's inflationary epoch. These fluctuations were remarkably small, only about 1 part in 100,000 variation in density from place to place. But gravity, given time, amplifies even tiny density contrasts. Regions slightly denser than average pulled in more material, becoming denser still, while regions slightly less dense had material pulled away, becoming voids. This process proceeded imperceptibly at first, guided primarily by dark matter whose gravitational influence drew ordinary hydrogen along for the ride. The hydrogen fell into the gravitational wells created by dark matter halos, forming increasingly concentrated clouds. Webb cannot observe the Dark Ages directly, no light existed then for the telescope to detect, but it can observe the immediate aftermath, the era called Cosmic Dawn, when the first stars ignited and began illuminating their surroundings. These population 3 stars formed from pristine hydrogen and helium, likely growing to enormous masses due to the inefficient cooling of primordial gas. Theory suggests they formed in small dark matter halos with masses equivalent to millions of suns, far smaller than the halos that would later host galaxies. The first stars might have formed in isolation or small groups, scattered throughout the universe in halos that collapsed first. The transition from darkness to light didn't happen instantaneously across the universe. Instead, it proceeded in patches as different regions reached the critical density needed to trigger star formation. Some halos collapsed early, others later. The first stars blazed to life in their isolated corners of the cosmos, creating bubbles of ionized hydrogen around themselves. These bubbles expanded as ultraviolet radiation from the stars ionized neutral hydrogen, but between bubbles darkness persisted. The universe during cosmic dawn resembled Swiss cheese ionized bubbles scattered through a neutral hydrogen medium, gradually growing and merging as more stars formed. Webb's observations of galaxies at redshifts above 10 provide glimpses into the final stages of this transition. These early galaxies represent regions where enough stars had formed to create bright, persistent light sources. The galaxies Webb detected aren't the very first stars. Those population 3 objects remain too faint and too rare for even Webb to see directly. Instead, Webb observes slightly later structures where numerous stars had already assembled into proto-galactic systems. These observations constrain when cosmic dawn occurred and how rapidly it progressed. If bright galaxies existed at redshift 13, corresponding to 300 million years after the Big Bang, then the first stars must have formed earlier still, perhaps at redshift 20 or 30, when the universe was only 100 to 200 million years old. The Dark Ages ended through a process called reionization, where ultraviolet radiation from stars and possibly early black holes reionized the hydrogen that had been neutral since recombination. This reionization proceeded gradually over hundreds of millions of years, with ionized bubbles growing and merging, until eventually all the hydrogen in the universe became ionized again, the state it remains in today. Webb's observations suggest reionization might have begun earlier, and proceeded faster than previous estimates suggested. Detecting bright galaxies at very high redshifts implies abundant sources of ionizing radiation existed early, capable of creating and sustaining large ionized regions. The spectrum of light from distant galaxies carries signatures of the neutral hydrogen it passed through. As light travels from a distant galaxy toward Earth, it encounters hydrogen clouds along the way. Neutral hydrogen absorbs light at specific wavelengths, creating absorption features in the galaxy's spectrum. The pattern of these absorptions reveals what fraction of the hydrogen along the line of sight was neutral versus ionized. Webb's spectroscopy of high redshift galaxies shows these absorption patterns, allowing astronomers to map the reionization process to see which patches of the universe have been ionized, by which epoch and which regions remain neutral longer. Understanding the Dark Ages matters because this period set the initial conditions for everything that followed. The first stars created the first heavy elements, enabling later generations of stars to form with different properties. The first galaxies established the framework for hierarchical assembly that built larger galaxies over billions of years. The reionization of hydrogen fundamentally changed the thermal state of the intergalactic medium, affecting how gas could cool and collapse into later structures. Webb's illumination of this previously inaccessible epoch reveals not just what happened, but how quickly, providing crucial constraints on the processes that transform the universe from darkness into the light-filled cosmos we inhabit today, where stars shine in billions of galaxies across billions of light-years. Formation crisis. Theoretical frameworks that had successfully explained galaxy formation across billions of years of cosmic history suddenly found themselves unable to account for what Webb observed in the universe's opening act, exposing fundamental gaps in our understanding of how matter assembles into galaxies. The crisis wasn't merely that observations contradicted predictions. Science thrives on such contradictions, using them to refine theories. The crisis was that no simple adjustment to existing models could reconcile the observations with known physics. Each attempt to fix one problem created others, suggesting the issue ran deeper than parametric tweaking could address. The standard galaxy formation paradigm, refined over decades, rests on a foundation called hierarchical assembly. Small dark matter halos form first as quantum fluctuations from the early universe grow through gravitational amplification. These halos trap ordinary matter, hydrogen and helium gas, which cools and collapses into the halo centers. When gas densities and temperatures reach critical thresholds, star formation ignites. Small halos merge into larger ones, building progressively bigger galaxies through a process that naturally produces the range of galaxy sizes and types we observe today. This bottom-up construction explains why dwarf galaxies are numerous, why giant ellipticals are rare, why spiral galaxies have the structures they do, and why galaxy clusters organize the way they do. Webb found massive galaxies at epochs when only the smallest halos should have assembled. The hierarchical model explicitly predicts that building large structures takes time. You need multiple generations of mergers to accumulate enough mass. A galaxy containing 10 billion solar masses of stars requires either that a correspondingly massive dark matter halo assembled early, which conflicts with structure formation timescales, or that small halos merge with extraordinary efficiency, converting their gas into stars far more effectively than any modern galaxy manages. Neither option fits comfortably within standard theory. Computer simulations of galaxy formation provide the primary tool for testing theoretical predictions. These simulations start with initial conditions matching the observed early universe, the density fluctuations mapped by cosmic microwave background observations, and evolve them forward using known physics. Gravity pulls matter together, gas cools through radiation, stars form when gas reaches sufficient density, supernovae and stellar winds heat and expel gas, regulating further star formation. These simulations successfully reproduce the distribution of galaxy masses, sizes, and morphologies in the present-day universe. They've been validated against observations of galaxies at various redshifts, showing that the basic hierarchical framework works. When researchers ran these same simulations forward to match Webb's observing epochs, redshifts of 10, 12, 13, the simulated universes looked nothing like what Webb observed. Simulations predicted mostly small, irregular proto-galaxies with low stellar masses and minimal structure. Webb found substantial galaxies with organized morphologies and significant stellar populations. The discrepancy couldn't be dismissed as minor in some cases. observed galaxies were 10 to 100 times more massive than the most massive galaxies in simulations at comparable epochs. Astrophysicists attempted various modifications to bring simulations into agreement with observations. One approach boosted star formation efficiency, allowing gas to convert into stars faster. This produced more massive early galaxies but triggered problems with feedback. Efficient star formation generates many supernovae, and supernova explosions heat and expel gas from galaxies, temporarily halting star formation. Increasing star formation efficiency without correspondingly increasing feedback leads to galaxies that consume all their gas too quickly, leaving no reservoir for later star formation. Increasing both star formation and feedback in tandem prevents galaxies from growing as large as observed. The parameters couldn't be tuned to satisfy all constraints simultaneously. Another modification adjusted the initial mass function, the distribution of stellar masses at birth. By preferentially forming massive stars, galaxies could achieve higher luminosities with less total stellar mass, potentially explaining why early galaxies appear overluminous. But massive stars die quickly, and their deaths produce distinctive chemical signatures. The observed chemical abundances in Webb's early galaxies don't match patterns expected from top-heavy mass functions. Additionally, top-heavy populations would generate intense feedback that should disrupt further star formation, again creating conflicts with observations of sustained star formation in these galaxies. Some researchers explored modifications to dark matter physics itself. If dark matter particles had even weak self-interactions, the ability to scatter off one another, this might accelerate halo assembly in the early universe without contradicting constraints from observations of later epochs. Self-interacting dark matter remains speculative, and introducing new physics to solve one problem risks breaking the many successful predictions of standard cold dark matter models. Each proposed solution required weighing the cost of adding complexity against the benefit of explaining Webb's observations, and in most cases, the costs seemed prohibitively high. The formation crisis highlighted how galaxy formation theory, despite its successes, remains incomplete. The simulations that work so well for lower redshift galaxies rely on subgrid models, simplified prescriptions for physical processes that occur below the resolution of simulations. How exactly gas cools and fragments into stars, how stellar feedback couples energy into surrounding gas, how black holes grow and influence their host galaxies. These processes happen on scales too small for cosmological simulations to resolve directly, so they're approximated through parameterized models calibrated against observations. Webb's discoveries revealed that these prescriptions, tuned to match lower redshift galaxies, break down in the early universe where conditions differ substantially from anything observable until now. Distant mirrors. Observing galaxies at extreme redshifts offers more than a view of distant objects. It provides a reflection of cosmic conditions when the universe itself existed in a state so different from today that the comparison spans not just distance but fundamental regime, where the rules governing structure, chemistry, and evolution operated under constraints that no longer apply anywhere in the modern cosmos. These ancient systems exist in a universe that was hotter, denser, smaller, and chemically simpler, where the gaps between galaxies measured mere millions rather than billions of light years, where dark matter halos were still actively assembling through violent mergers, and where every star that formed represented a pioneering venture into chemical territory the universe had never explored. The light Webb captures from these distant galaxies departed on its journey more than 13 billion years ago, travelling through expanding space while the universe grew around it. During this journey, the galaxies themselves continued evolving, many of them likely merged with others, built more stars, and transformed into structures that might exist in the modern universe as mature ellipticals or spiral galaxies not so different from the Milky Way. We see only their infancy, frozen in time by the speed of light. The light carries information about that specific moment in their history, encoding details about their stellar populations, gas chemistry, and physical conditions through spectral signatures that astronomers can decode. This temporal displacement creates a peculiar situation. Webb observes a galaxy as it was 300 million years after the Big Bang, but that galaxy, if it survived, if it didn't merge destructively with another, has continued evolving for 13 billion years since emitting the light we now detect. Somewhere in the modern universe, perhaps within a few 100 million light-years of Earth, the descendants of Webb's high-redshift galaxies exist as mature systems. We cannot identify which modern galaxies descended from which early galaxies because cosmic expansion has scattered them across vast distances, and 13 billion years of merger history has erased any recognizable connection between ancient progenitor and modern descendant. The reflection works both ways. By studying early galaxies, astronomers learn about the conditions from which all galaxies, including our own, emerged. The Milky Way began as something like the compact, actively star-forming systems Webb observes at high redshift. Our galaxy's oldest stars, those in the halo and bulge with ages exceeding 12 billion years, formed during the epoch Webb now studies. The chemical signatures in these ancient stellar populations, their deficiency in heavy elements, their unusual abundance ratios reflect the environment of the early universe, when metal-poor gas was just beginning to be enriched by the first generations of stellar death. Webb's observations provide context for these local fossils, showing what conditions were like when and where they formed. The chemistry tells particularly revealing stories. Heavy elements in the universe form through stellar nucleosynthesis. Stars fuse lighter elements into heavier ones, then disperse these products through stellar winds and supernova explosions. Each element forms through specific nuclear reactions that require particular temperatures, pressures, and timescales. Oxygen forms readily in massive short-lived stars. Carbon and nitrogen require intermediate mass stars and longer timescales. Iron comes primarily from type Ia supernovae, which take hundreds of millions to billions of years to occur. The relative abundances of these elements in a galaxy's spectrum thus encode information about which types of stars have lived and died, how long ago, and in what proportions. Webb's spectroscopy revealed that early galaxies had already accumulated surprisingly diverse chemical inventories. Some showed oxygen to hydrogen ratios, approaching 1/10 the solar value, remarkable for objects existing just hundreds of millions of years after the Big Bang. The presence of carbon and nitrogen in certain spectra implied contributions from intermediate mass stars, suggesting these galaxies had undergone multiple generations of star formation, with sufficient time between generations for stars of various masses to complete their life cycles. These chemical signatures provided some of the strongest evidence that galaxy evolution proceeded far more rapidly in the early universe than standard models predicted. The morphologies of distant galaxies offer additional insights. Many of Webb's high redshift objects appeared compact, with stellar masses concentrated into regions just a few thousand light-years across, far smaller than comparable mass galaxies in the modern universe. This compactness reflects the higher densities of the early universe. When galaxies were closer together and dark matter halos were still assembling, galaxies experienced more frequent gravitational interactions that could compress their stellar distributions. Over billions of years, these compact cores would expand through various dynamical processes, minor mergers adding mass to outer regions, stellar orbits gradually spreading due to gravitational scattering, gas accretion building extended disks. The compact early galaxies thus represent compressed versions of later galaxies, containing similar stellar masses but in much smaller volumes. Studying these distant mirrors teaches humility. The universe's early chapters proceeded through processes and under conditions we cannot recreate, driven by physics we thought we understood but clearly didn't comprehend completely. Each high redshift galaxy Webb observes represents a data point constraining theories of cosmic evolution, but also a reminder of how much complexity emerged in those first few 100 million years, complexity that determined everything about the universe's subsequent 13 billion year history, including the eventual formation of a galaxy containing a star with planets where creatures evolved capable of looking back through time and seeing, however imperfectly, the ancient cosmos from which they ultimately descended. Photon journey. Individual photons that Webb's mirrors collect and focus onto its detectors have been travelling through expanding space for over 13 billion years, carrying information encoded at the moment of their emission from stars that may no longer exist in galaxies that have long since merged into larger structures we cannot identify. Each photon began its journey as ultraviolet, or visible light, emitted when an electron in some atom transitioned between energy levels, releasing its excess energy as electromagnetic radiation. The photon departed its source galaxy travelling at light speed, as all photons must, heading outward into the surrounding space. But space itself wasn't static during this journey. The universe has been expanding since the Big Bang, and this expansion affects light travelling through it. As space stretches, the wavelength of light stretches proportionally. A photon that started as ultraviolet, with a wavelength of 300 nanometers, becomes visible blue light at 400 nanometers, then yellow, then red, then infrared as the expansion continues. This redshift isn't due to the photon losing energy in any conventional sense. It's a consequence of the changing geometry of space-time itself. The photon's wavelength is literally stretched by the expansion of the medium through which it travels. The degree of stretching provides a direct measure of how much the universe has expanded during the photon's flight. A redshift of 13, like that observed for glass, Z13, means the universe has expanded by a factor of 14 between emission and detection. Wavelengths are 14 times longer than when emitted, and the universe is 14 times larger. This expansion factor, combined with models of how expansion rates have changed over cosmic history, allows astronomers to calculate when the photon began its journey. For redshift 13, that calculation yields approximately 300 million years after the Big Bang, placing the source in the universe's earliest epochs. The photon's journey wasn't straightforward. It passed through varying densities of matter and dark energy, each affecting space-time's geometry differently. In the early universe, when matter dominated, expansion decelerated gravity from all the matter in the universe, pulled everything together, fighting against the initial expansion. Later, as expansion diluted matter density, dark energy came to dominate, causing expansion to accelerate. The photon experienced these changes in expansion rate, its redshift accumulating faster during some epochs than others. The relationship between redshift and distance or time isn't linear, it depends on the entire expansion history. During its journey, the photon occasionally encountered matter. Hydrogen atoms along the line of sight could absorb it if its wavelength matched one of hydrogen's absorption lines. But as the photon redshifted, it continuously changed wavelength, passing through hydrogen's absorption features. Some photons get absorbed this way, creating the characteristic absorption patterns seen in distant galaxy spectra. The photons that reached Webb managed to avoid absorption, threading through billions of light-years of space without encountering an atom whose energy levels match their constantly shifting wavelength. The photon also passed through the epoch of reionization, when the first stars ionized the neutral hydrogen filling space. Before reionization, neutral hydrogen would have absorbed photons at specific wavelengths quite efficiently. After reionization, most hydrogen became ionized, making space largely transparent to ultraviolet and visible light. The photons Webb detects from the earliest galaxies inform us about reionization's timing and progression. Their spectra show how much neutral hydrogen remained along different lines of sight at different epochs. Gravitational fields along the journey bent the photon's path. Massive galaxy clusters sitting between source and observer act as gravitational lenses, their space-time curvature deflecting passing light. Some of Webb's high redshift discoveries were magnified by such lensing, their light brightened and their apparent size enlarged by the gravitational optics of foreground clusters. Without this natural magnification, many of Webb's most distant galaxies would have been too faint to detect even with the telescope's extraordinary sensitivity. The photon that finally reached Webb entered the telescope's optical path, reflected off one of the 18 hexagonal mirror segments, bounced through the secondary and tertiary mirrors, and focused onto a detector in one of Webb's infrared instruments. There, it struck a sensitive material designed to register individual photon arrivals, transferring its energy and triggering an electronic cascade that got recorded as data. That data, combined with millions of other detected photons, formed the spectrum or image that astronomers analysed, revealing the properties of the distant galaxy from which these photons originated. The information carried by these photons proved astronomers wrong about the early universe, showing galaxies where none should exist, maturity where only simplicity was expected, chemical enrichment that shouldn't have occurred yet. The photons themselves are neutral messengers. They don't care about theoretical predictions or cosmological models. They simply carry information about the conditions where and when they were emitted, traversing cosmic expanses to deliver news from an ancient epoch. That the news contradicted expectations isn't the photons' fault. It's a reflection of how incomplete our understanding was before these particular messengers arrived after their 13 billion year journey, to tell us we'd gotten important details wrong about the universe's opening chapters. Timeline collapse. Causality in the early universe faces severe challenges when multiple processes that should have occurred sequentially appear to have happened nearly simultaneously, creating temporal contradictions that suggest either our timeline is wrong or multiple independent processes, all accelerated beyond physical plausibility. The standard cosmic timeline allocates specific periods for each major evolutionary stage. First stars form by 200 million years, first galaxies assemble by 400 million years, substantial chemical enrichment occurs by 800 million years, mature galactic structures develop by 2 billion years. These stages build on one another. Each requires the previous stage to complete before proceeding. Stars must form before they can die and enrich their surroundings. Enrichment must occur before second-generation stars can form with the metals needed for efficient cooling. Multiple generations must cycle before significant chemical diversity develops. Webb observed galaxies at 300 to 400 million years, showing evidence that all these stages had already occurred. The presence of heavy elements required stars to have formed, evolved, and died. The diverse chemical abundances suggested multiple stellar generations with different masses and lifetimes had contributed their nucleosynthetic products. The organized morphologies implied dynamical relaxation over many orbital periods. The substantial stellar masses demanded sustained star formation over extended periods. All of these processes, which the standard timeline spreads across hundreds of millions to billions of years, appeared compressed into the first few 100 million years. The mathematical problem becomes clear when you calculate timescales. Population 3 stars, the first generation, likely lived only a few million years given their expected enormous masses. Their deaths would enrich small regions around them, enabling population 2 star formation. But population 2 stars span a range of masses, and different masses have different lifetimes. Massive stars die in 10 to 20 million years. Intermediate mass stars take 100 million to 1 billion years. Low mass stars live for tens of billions of years. The chemical signatures Webb observed required contributions from multiple mass ranges, implying that stars across this range had formed, and at least the massive and intermediate mass ones had died. Consider carbon and nitrogen, elements whose abundances relative to oxygen serve as chemical clocks. Carbon forms primarily in intermediate mass stars through helium burning, but these stars don't return their carbon to the interstellar medium until they reach the asymptotic giant branch phase of evolution, typically after hundreds of millions of years. Nitrogen requires even longer, forming through CNO cycle processing in stellar interiors and returning to the interstellar medium through stellar winds or final mass loss. Detecting carbon and especially nitrogen in galaxy spectra at redshift 12 implies these slow processes had already completed, yet the universe was only 350 million years old at that redshift. The timeline problem extends beyond chemistry to structure formation. Galaxies don't appear instantly as organized systems, they build through hierarchical mergers of smaller structures. Each merger takes time. The halos must approach each other through gravitational attraction. Orbital decay through dynamical friction drags them together, tidal forces strip material, and eventually the systems coalesce. This process typically requires several hundred million years for each major merger. Building a galaxy containing 10 billion solar masses through mergers of smaller proto-galaxies, each contributing perhaps 100 million to 1 billion solar masses, requires multiple merger generations. The arithmetic quickly exceeds available time. Dynamical evolution imposes additional constraints. When two galaxies merge, the result is initially irregular, and kinematically hot stellar velocities are random rather than organized. Settling into a stable configuration with coherent rotation or regular morphology requires time for phase mixing, violent relaxation, and orbital averaging. These processes depend on stars completing multiple orbits, and orbital periods in the early, compact systems observed by Webb would be 10 to 20 million years. Achieving the morphological regularity some of Webb's early galaxies display requires many orbital periods, suggesting ages of 100 to 200 million years just for dynamical settling time that must be added to the formation and enrichment timescales. Some researchers propose that processes in the early universe operated fundamentally faster than in the modern cosmos. Perhaps the first stars formed more efficiently because initial density fluctuations were stronger than expected. Perhaps star formation converted gas into stars at unprecedented rates because feedback mechanisms hadn't yet developed. Perhaps mergers happened more frequently in the denser early universe, accelerating hierarchical assembly. Each of these proposals offers partial relief, but creates new tensions with other observations or physical constraints. The simultaneity problem crystallizes when considering that Webb observes multiple early galaxies at similar redshifts showing similar maturity. This isn't just one anomalous object that might represent a statistical fluke or unique circumstances. It's a population of early, mature galaxies suggesting that whatever processes enabled rapid evolution operated widely across the universe. The statistical argument becomes powerful. If mature galaxies are common at high redshift, then the processes creating them must be robust and repeatable, not contingent on rare, special conditions. This prevalence implies that the timeline collapse represents normal early universe evolution, not exceptional cases, forcing a wholesale reconsideration of the temporal ordering of cosmic structure formation. Reality check. When observations force revisions to cosmic timelines, the consequences ripple outward from astronomy into fundamental physics, calling into question not just when events occurred, but whether our understanding of time, gravity, and matter itself accurately describes reality. The early universe serves as a physics laboratory inaccessible through any other means. Conditions that existed 300 million years after the Big Bang cannot be recreated on Earth or simulated with complete confidence. We rely on observations to tell us how physics operates under those extreme conditions, and when those observations contradict predictions derived from our best physical theories, we face an uncomfortable choice. Either the observations are wrong, or the theories are incomplete. The lambda CDM model, which successfully explains so much of cosmic evolution, rests on general relativity for its description of gravity and spacetime, quantum field theory for its treatment of matter and energy, and thermodynamics for processes like gas cooling and star formation. These frameworks have been tested extensively in terrestrial laboratories and astronomical contexts ranging from solar system dynamics to binary pulsar timing. They work. Yet applying these same frameworks to the early universe, using equations and parameters that succeed everywhere else, produces predictions that Webb's observations flatly contradict. The discrepancy suggests that something in our theoretical edifice breaks down under early universe conditions. General relativity describes gravity as space-time curvature caused by mass and energy. The equations work beautifully for describing planetary orbits, gravitational lensing, black hole behavior, and the expansion of the universe itself. But general relativity operates under assumptions that space-time is smooth at large scales, that gravity's strength remains constant, that the equivalence principle holds universally. If any of these assumptions fail in the early universe's extreme conditions, the predictions derived from general relativity would be wrong. Some theoretical physicists have proposed modifications to gravity that only become apparent at very early times or very large scales, potentially allowing structure to form faster than standard general relativity predicts. The cosmological constant, the term representing dark energy in Einstein's equations, might not be constant at all. In the standard model, dark energy's density remains fixed while matter density dilutes as the universe expands, causing dark energy to dominate over time. But if dark energy evolved differently in the early universe, perhaps starting with lower density and increasing later, expansion rates would differ from current predictions. This would affect every cosmic distance, scale, and timeline, potentially reconciling observed early galaxy maturity with available time. Testing such modifications requires observations spanning cosmic history, comparing predictions against data from multiple epochs, and Webb's early universe observations provide crucial new constraints. Particle physics enters the discussion through the Standard Model, which describes matter and radiation using quantum field theory. This framework predicts how particles behave at high energies, how they interact, and how they cool and condense as the universe expands. The first stars should have formed from primordial hydrogen and helium following cooling processes described by atomic physics and thermodynamics. If quantum mechanics operates differently at the energy scales characteristic of the very early universe, or if unknown particles existed then that don't exist now, the cooling rates and star formation timescales could differ from standard predictions. No direct evidence supports such modifications, but the gap between predictions and observations creates space for speculation about physics beyond the Standard Model. Dark matter, which dominates gravitational dynamics throughout cosmic history, remains mysterious. We know it exists through its gravitational effects, but don't know what it's made of. The lambda CDM model assumes cold dark matter particles that move slowly compared to light speed and only interact gravitationally. But dark matter could have weak self-interactions, allowing dark matter particles to scatter off one another and slightly alter how dark matter halos assemble. These interactions might accelerate halo formation in the early universe without contradicting observations from later epochs where halo dynamics are well constrained. Exploring such possibilities requires balancing the desire to explain Webb's observations against the risk of introducing unnecessary complexity. The scientific method requires that theories make testable predictions, and when observations contradict those predictions, theories must be revised or replaced. The history of physics includes numerous examples where observations revealed gaps in understanding Mercury's orbit, pointing toward general relativity's need, stellar spectra demanding quantum mechanics, galaxy rotation curves requiring dark matter. Webb's early galaxy observations may represent another such moment, where nature teaches us that our theories, while successful in many domains, fail to capture some essential aspect of reality. The question becomes whether the required modifications are minor adjusting parameters within existing frameworks or fundamental, demanding new physics. Scientists approach this dilemma cautiously. Extraordinary claims require extraordinary evidence, and before abandoning well-tested theories, researchers exhaust possibilities within existing frameworks. Perhaps astrophysical processes we understand poorly, like the first star's properties or early black hole growth, can explain observations without modifying fundamental physics. Perhaps systematic errors in observations or their interpretation account for apparent discrepancies. These more conservative explanations deserve thorough investigation before invoking new physics. But if conservative approaches fail, if no combination of astrophysical adjustments reconciles theory and observation, then physics itself must evolve to accommodate what the universe insists is real, regardless of how uncomfortable that reality might be for theories we've come to trust. New beginning. Astronomy stands at a threshold where the first chapter of cosmic history requires complete rewriting, not mere revision, because Webb's observations have revealed that the narrative arc, from simplicity to complexity, proceeded along a path dramatically different from the one generations of cosmologists carefully constructed from decades of observation and theory. The old story began with darkness, a universe cooling from the Big Bang, its primordial gas gradually settling into the first dark matter halos where, after 100 to 200 million years of patience, the first stars finally ignited. These population 3 stars lived briefly, died violently, and seeded their surroundings with the first heavy elements. Over the next few 100 million years, small proto-galaxies assembled from these enriched regions, merging gradually into larger structures over billions of years, eventually producing the majestic spirals and ellipticals that populate the modern universe. This narrative had aesthetic appeal. It felt right, matching intuitions about how complex structures emerge from simple beginnings through patient, incremental processes. Nature rarely rushes. Evolution, whether biological or cosmic, requires time. The old story respected these intuitions, placing galaxy formation on timescales that felt proportional to the magnitude of the transition from diffuse gas clouds to organized galactic systems. Webb's observations violently disrupted this comfortable narrative by showing that the early universe apparently didn't share human intuitions about appropriate timescales for complexity to emerge. The new beginning must start earlier and proceed faster. If galaxies with billions of solar masses existed at 300 million years, as Webb demonstrates, then the first stars formed substantially earlier, perhaps 100 million years or even less after the Big Bang. These first stars must have been numerous enough and distributed widely enough to create the chemical enrichment Webb observes. They must have formed in environments that allowed rapid subsequent star formation, not blown their host halos apart with feedback as simple models suggest. The first dark matter halos must have assembled faster than hierarchical structure formation naturally allows, or gas must have collapsed into stars far more efficiently than modern galaxies achieve. The new narrative must accommodate dramatic acceleration in multiple processes simultaneously. Star formation efficiency in the early universe might have exceeded modern rates by factors of 10 or more. Chemical enrichment must have proceeded rapidly, with stellar generations cycling through formation, evolution, and death on compressed timescales. Galaxy assembly must have occurred through more efficient mergers or higher accretion rates than later epochs display. Each acceleration requires explaining why the early universe operated so differently from the modern cosmos, what physical conditions enabled these enhanced rates, and why efficiency declined over cosmic history. One emerging picture suggests the early universe existed in a fundamentally different state, denser, hotter, more turbulent, where processes that later became gentle and gradual operated with intense vigour. Gas colliding at high velocities shocked into rapid star formation. Dark matter halos still growing through continuous mergers kept their gas supplies replenished. The universe's smaller size meant galaxies encountered each other frequently, triggering bursts of star formation through tidal interactions. Chemical enrichment happened in intense bursts rather than slow accumulation, with massive stars forming preferentially and dying quickly, flooding their environments with metals that immediately catalyzed further star formation. This picture makes the early universe sound chaotic, and perhaps it was. The modern cosmos appears relatively sedate galaxies separated by vast distances, evolving in relative isolation, star formation proceeding at modest rates. The early universe may have been more like a cosmic storm, with matter cycling rapidly through different phases, structures forming and dissolving in geological instants, the entire system far from equilibrium. This turbulent state would naturally produce the accelerated evolution Webb observes, but it demands explaining how the universe transitioned from this frenetic early phase to its current tranquility. The implications extend beyond rewriting textbooks. The new beginning affects our understanding of how galaxies like the Milky Way formed. If the early universe was this active, then the Milky Way's oldest stars, those in the halo and thick disk with ages exceeding 12 billion years, formed in conditions more extreme than previously imagined. The chemical signatures these ancient stars carry encode information about the chaotic environment of their birth. Studying them with this new perspective might reveal details about early universe conditions that Webb's distant observations cannot access directly. The rewritten first chapter also affects predictions about galaxy populations throughout cosmic history. If large galaxies assembled early, they should have undergone different evolutionary paths than the gradual growth standard models predict. Merger histories would be compressed into earlier epochs. The transition from irregular morphologies to organized spirals and ellipticals might have occurred faster. The relationship between galaxy mass and age could differ from current assumptions. Testing these predictions requires systematic surveys of galaxies across redshift, comparing populations at different epochs to trace evolutionary pathways. Perhaps most profoundly, the new beginning challenges assumptions about the predictability of cosmic evolution. The old story suggested that given initial conditions and physical laws, cosmic history unfolded inevitably along a single trajectory. The early universe's apparently rapid evolution suggests that outcomes may depend sensitively on conditions in ways we hadn't appreciated, that the universe's first few 100 million years represented a critical period, where small variations could produce dramatically different outcomes. This sensitivity would make the early universe harder to model, but also more interesting, a time when the cosmos's future hung in balance, when slightly different conditions might have produced a universe looking nothing like the one we inhabit, where we evolved to look back and try to understand where we came from.